Hello, hello, welcome back. In this video, I will start a series on partial differential equations. My plan for this video series is to work through many of the solution techniques in this book, Solution Techniques for Elementary Partial Differential Equations, second edition by Christian Constanda. Dr. Constanda is a professor at the University of Tulsa, who's actually my advisor for my master's program in applied math. He writes an excellent book. So I'm just going to work through some of the solution methods that he discusses in the book. And the first one is this Fourier series. We're going to talk about computing a full Fourier series. And basically what this is, which is a new expansion of a function f. And then we'll talk about convergence issues, and then we'll look at some background definitions that are necessary to have that discussion. And then we'll look at our first example. So remember in Calculus 2, you've seen expansions of functions before. In Calc 2, we talked about the Taylor series of a function about a point x0. We said that if that function f is infinitely differentiable, so we can compute all of the derivatives at x0, this infinitely differentiable function f can be expanded in a Taylor series around the point x0 in an interval where the function f is defined. And this was the Taylor series. We have f of x. It would correspond to a series of this form. We have the sum as n goes from 0 to infinity of the nth derivative of f evaluated at x0 divided by n factorial times x minus x0 to the nth power. So this is, well, the 0th derivative evaluated at x0 is just the original function times x minus x0 to the 0. And of course, 0 factorial is 1. If we substitute in n equals 1, we have got the first derivative evaluated at x0 times x minus x0. Then we'll have the second derivative evaluated at x0. Oops, that should be an x0, not a 2. Divided by 2 factorial, which is 1/2, times x minus x0 squared. And we keep going. So this is n equals 0, n equals 1, n equals 2. When n equals 3, we'll have 1 over 3 factorial. 3 factorial is 3 times 2 times 1, so we'll have a 1/6 there. We'll have the third derivative evaluated at x0. Times x minus x0 to the third, and you continue in this way for a long time. Now, if we have the function f, and we are assuming that we have that function f, you can compute f of x0, f prime of x0, f double prime of x0, if you can find a pattern for that nth derivative, and then evaluate it at the point x0. So provided all those derivatives exist, and that's why we need an infinitely differentiable function, all you have to do is substitute those values in. And then this x minus x0 is a multiplier. So as we go from term to term, we've got x minus x0 squared, x minus x0 cubed. For the n equals 0, or for the nth term in the series, you're going to have x minus x0 to the n. So if n is 10, it's going to be x minus x0 to the 10th. But that's generally given as well. Now, under certain conditions, this converges to f pointwise. This infinite series actually gives us f back for each x value. In some interval centered at x0. And an open interval typically. And it may or may not converge at the endpoints of that interval. In that case, rather than using this tilde and saying that this Taylor series was generated by this function, we'll say that they're actually equal to each other, and we'll put an equal sign there. So we've done this before. If you've taken Calculus 2, you've seen this before. Here's an example. E to the x turns out to have this Maclaurin series, which is just this Taylor series centered at x equals 0. So when n equals 0, we get x to the 0 over 0 factorial, which is just 1. When n equals 1, we get x. When n equals 2, we have 1 over 2 factorial times x squared. That's 1/2 x squared. Then we've got 1 over 3 factorial, which is 6 times x cubed, and so on. 1 over 4 factorial times x to the 4th, and you keep going. It turns out that this infinite series converges to e to the x for every x value from negative infinity to infinity. So this will always give you e to the x back. Now you can think of this as a weighted average. You can say if I've got a 1 plus 1 of these, and 1/2 of these, and 1/6 of these, and 1/24 of that, I can take a weighted average of these polynomial functions. And with these weights, I'm actually going to get that function e to the x back. So that's pretty cool. That's very powerful. Fourier series are very similar, but rather than taking a weighted average of x to the 0 and x to the 1st and x squared and x cubed and x to the 4th, like we're doing right here or right here, rather than taking a weighted average of x minus x naught to the nth power for different values of n, we're going to take a weighted average of cosine and sine functions with different associated periods, or the period corresponds to a particular frequency. So we're going to have cosine and sine functions of different frequencies. We're going to take a weighted average of those and add all of those together, add a constant, and that will, under certain conditions, give us our function back. That is sort of the idea of a Fourier series. So I'll say a weighted average of sinusoidal functions with different frequencies. And if you have a different period, you have a different frequency. So here is the expansion. If you have a function f, its Fourier series is 1/2 of a naught plus the sum as n goes from 1 to infinity of a sub n, that's a constant that we'll be able to solve for n equals 1 through infinity, times cosine of n pi x over L plus b sub n times sine of n pi x over L. So our goal in this section is to be able to come up with a Fourier series for a given function f. And first we're going to find, or we'll start with a function f, and then we'll look at what's called its periodic extension, because we want sort of a version of the function f that repeats itself every certain number of units in the x direction. And then because we have this version of the function of f that repeats itself, it would make sense to talk about taking this weighted combination of sine and cosine functions to get that function f back. Here, L is just a positive constant. And your a sub 0, a sub 1, a sub 2, a sub 3, a sub n for n equals 1 through infinity, and b sub n are just constants. They're constant coefficients. And you can think of those like the coefficients of e to the, or you can think of those like the coefficients of the powers of x that we have right here. So we have a coefficient of 1, a 1, a 1/2, a 1/6, a 1/24. Like those are the weights in your weighted average. It's like having a recipe and you have, 2 eggs and a cup of milk or something like that. You're going to have different measurements of like different ingredients for your recipe. In the same way, we're going to have different measurements for different functions here with a Taylor series. And the same would be true down here, but we're taking not powers of x this time, but sinusoidal functions with different frequencies. And we'll talk more about those frequencies and what each of these functions means in a little bit. So let's look at a few definitions. Probably already know this one. We say that a function f is periodic. This is f defined on the real line. It's periodic if there exists a t, and that backwards e means there exists, greater than 0, such that f of x plus t is equal to f of x for all x in the reals. The smallest number t for which that is true is called the fundamental period, or just the period of the periodic function. And of course, I could add that n times. If it repeats every t, it's going to repeat every nt, where n is a positive integer. Sort of obviously, that's true. That's for any natural number n. So those are our counting numbers, 1, 2, 3, and so on. And for all x in the reals. Now we already know that our sine and cosine functions are periodic with period 2 pi. We know sine of x looks like this. It starts at 0, then at pi over 2, it goes to its max. Then it comes back to 0, and at 3 pi over 2, it goes to its min. And then it goes back to 0. And it does that in both directions. Forever, it just continues. Didn't do a very good job with my sine wave, but hopefully you get the idea. That's negative pi over 2 there, and that's pi there. This is typically what we think of as our one period or a single cycle of that sine wave. So it's just doing that, and then it repeats. So we know that sine of x plus 2 pi is equal to sine of x for all x in the reals. That upside down a represents for all x in the real number system. And obviously, if I added 2 pi times n, that would be true as well. So if n was 2, this is just saying that, well, it's going to repeat every 4 pi as well. So I could take that version of it that's twice as long, and that would repeat. Or I could do a sine of x plus 2 pi plus another 2 pi plus another 2 pi. Every time I add 2 pi, that's going to be fine. So the period is 2 pi, the smallest period, the fundamental period is 2 pi, but we could also say that sine of x plus 2 pi n is equal to sine of x for any natural number n and for all x in the reals. And of course, these are still true for a cosine function, which is over here. Now, cosine looks very similar. It starts at 1, and then it goes to 0, then it goes back to -1, then it goes up to 0, and then it comes back to 1. It's actually just 90 degrees off, or pi over 2 radians off from that sine function. And you can keep going like this. And this is what we traditionally think of as one period. That first period goes from 0 to 2 pi. And then that repeats. So we know that cosine of x plus 2 pi is equal to cosine of x, oops, for all x in the reals. And of course, it's going to repeat every 4 pi as well, and every 6 pi, and every, if I go backwards 2 pi, it would also work. So this is true whenever I add or subtract 2 pi as many times as I want, and as that number of times that I'd be adding or subtracting 2 pi. And I can always go back to that original cosine function on that first interval. This is for all x in the reals, and of course for any natural number n, those counting numbers. Now, these are just our basic sine and cosine waves. But we could manipulate those equations a little bit by writing them this way. Let's say we're not interested in just cosine of x, but maybe we're interested in cosine of n pi times the quantity x plus 2l over L. And we'll talk more about that n pi and that L and what they mean in a little bit. Now, if I distribute that n pi through the parentheses in the numerator, I get n pi x plus 2L times n pi is 2 pi n times L. And then all of that is divided by L. So I could divide each of these by L separately. And we see cosine of n pi x over L. And the L's reduce over here, plus 2 pi n. Well, that's just adding a multiple of 2 pi. Again, we're thinking of n as a natural number. So it's not a fraction. It's 1, 2, 3, 4, or actually, we could let n be any integer. N could be -1, -2, -3, -4. It could be 0. This is for, let's say, for any integer n. Well, adding that doesn't do anything to my cosine function. So I end up with n pi x over L. Now notice that over here, I've replaced my x with x plus 2L. And over here, I just have the x. So what this tells me is that the period of this cosine of n pi x over L is actually 2L. Because if I replace x with x plus 2L, I get exactly the same function back. So this tells me I've got cosine of n pi x over L. That's periodic. with period 2L. I didn't prove that that was the smallest period, but it turns out that that is the smallest period. Similarly, sine of n pi x over L is periodic with period 2L. Now, if I went back to trig class and I wanted to graph just one of these guys, I would think of this y equals this cosine function as a transformation of the cosine of x function. So basically, this is the cosine of x function, but I've changed the period. Now, the original cosine of x function was well-defined, or well, it's well-defined for all real numbers, but the original period, that original interval where cosines would repeat or went through one time to trace out one period, was 0 to 2 pi. That's the one we typically think of. So over here, when I'm trying to think about what this function actually means, it's helpful to think of this expression in the parentheses as lying between 0 and 2 pi. So I want to know, for which x values does this expression, which is the angle we're taking the cosine of, lie between 0 and 2 pi? Well, if I multiply all three sides of this compound inequality by L, I get this. If I divide all three parts of this by n pi, I get that. And so I have 0 is less than or equal to x, and the pi's reduce. And this is less than, oops, I forgot to multiply by L over here. This times L is going to be 0. This times L would be 2 pi L. So I'd have 2L over n. And you're saying to yourself, okay, well, what does that mean? Well, that means that this is the interval where we will trace out one cycle of this cosine function for a given value of n. So when n is equal to 1, we have y equals cosine of pi x over L. In that case, we're going to trace out one period of this function if n is equal to 1. We have one period traced out on the interval from 0 to 2L, because I'm replacing n with 1. And so what I would see is this. We know that cosine starts at its maximum. So I'd have a 1 there at the beginning. And its period is 2L. And so we have that pattern that we always see. Here's L in the middle. There's half of L. There's 3/4, or excuse me, 3/2 of L. And so we'd have it start at 1, then go back down to 0, then go to -1, then back up to 0, and then back up to 1 again. And this would repeat. Now, most of the time when we're talking about Fourier series, we're not going to look at the interval from 0 to 2L. We're going to look at the interval from -L to L. So if I wanted, I could go backwards over here to -2L and trace another one of these waves. And this is obviously not to scale. That interval should be the same length as that interval, and I made it a little bit smaller. Oops, that should only be -1L. But if I wanted to trace this out now, I could trace one period from 0 to 2L, but that's not what I want to do. When we're talking about Fourier series, we usually focus on the interval from -L to L. So I'm going to think of that as one period of my cosine of pi x over L. It goes from, and we're interested in that range, or excuse me, that interval of x values from -L to L. So we get one period traced out from when x is between 0 and 2L. That's over here, but then we sort of shift it. Rather than focusing here, we focus here. Now, if n is equal to 2, let's look at what happens. We've got cosine of 2 pi x over L. In that case, when I substitute n equals 2 into this equality, I get 0 to L. So we'll trace out one period for x between 0 and L. And that means that if I look at the interval from negative 2L to L, or excuse me, negative 2L to positive 2L, rather than having one period here like we did before, now we're going to have two periods traced out on the interval from 0 to 2L. So let's see. I want to draw two cosine functions from here. So I'd start there, and we'd split that in half. So we've got that. That's my first period, and then my second one would look like that. So I have one period on 0 to L, and that means two periods on this interval. And then we could go backwards as well. So I've got 4 periods graphed here. But if I just focus on the interval from negative L to L, which is what we'll tend to do, oops, we've got like 2 cycles of that cosine wave. I wrote a 2 here, that should be an L. So when n equals 1, we see 1 wave. When n equals 2, we see 2 waves. When n equals 3, we'll see 3 waves. So we'll have 3 pi x over L here. So we'll have one period traced out for x between 0 and 2L over 3. So if I'm on the interval from 0 to 2L, we're going to do that 3 times. I'll try to make this look a little bit better. Try to make it as even as possible, but sometimes that's hard to do. We do the best we can. I mean, I guess we could use graph paper, that would make it a little easier. But I'd want to split this into 3 intervals. Oops, that should be down here. And it look something like that. And over here, I want to try to split this into thirds as well. Cosine starts at the top. And it has its minimum here at the bottom, halfway in between. And then it would just go through that cycle. Now, if I'm looking again at the interval from negative L to L, because that's what we tend to be interested in with Fourier series, I've got this guy. It's a little bit hard to tell, but that's 1 wave, 2 waves, 3 waves. So if that n is equal to 3, that means you're going to see 3 cycles of that cosine function on this interval. So you've got 3 cycles here, you've got 2 cycles here, you've got 1 cycle here. And then let's look at that Fourier series expansion again. This says, take a little bit of this function, this first function. Take a sub 1 times this function, and a sub 2 times this function, and a sub 3 times that function. and do that for all the different cosine functions for different values of n. So n is going to go from 1 to infinity. As n increases, the number of waves in between that negative L to L will increase. So if n is equal to 10, we'd actually have 10 cycles between negative L and L. And we're saying, okay, how much of each of those cosine functions do we need? Provided that we're also taking these weights like of similar sine functions. How many of, or like how much of this and how much of this do we need for each value of n? So that when we add this to this, we sort of get the function back in some way. Now we'll talk about convergence later, but it's very similar to what we were talking about back here when we talked about Taylor series in calculus 2. We've got a weighted average of these. I've got one of these and one of these and a half of this function and a sixth of this function and 1/24 of that. So it's like the volumes in a recipe. If I combine those in just the right way with just the right measurements of ingredients, I get my e to the x back. The same is true here, but now we're talking about starting with functions that look like this, these sinusoidal functions. Now I just focused on the cosine functions, but the sine functions, excuse me, are very similar. They're just shifted a little bit. So these all have period 2L, as we showed right here, because this is equal to this, which is equal to this, which is equal to this. But what they are is they're cosine waves of different periods, and we want to know what combination of waves that looks like this will give us that original function back. So with that in mind, let's look a little bit more at the Fourier series. Let's say that f is defined on the interval from negative L to L. And just for our example, I'm going to give you this picture. It could be a different function. And I'm going to make it this one, where it's the 0 function between negative L and L, and it's the function y equals x between 0 and L over here. It's just for example. Oops, it should be an x. Then if I want to construct the periodic extension of this, I take not the entire thing, but I want to take f on the interval from negative L to L, not including negative L. That way I'm guaranteed to have a function. I don't want the function, or I don't want a relation that would have 2 values every once in a while. I want to use this interval from negative L to L, not including the left endpoint. If I want to extend this function periodically to the entire real line, we just choose to exclude that point. I guess that's an L, not a 1. That's x. So that's one period of that periodic extension. Then if I want to see another period of that over here, I would go out to 3L, because remember it repeats every 2L. And I would see that shape again. And I could show another period on this side, about to negative 3L. And we'll see that shape again. Okay. So that's the periodic extension. And of course, it goes on infinitely. You're going to see this over and over again. We want f of x plus 2l to equal f of x for all x in the real number system. And that will be true provided this pattern continues. We're just drawing 3 periods of it. Now that we've come up with a periodic extension, it makes sense to talk about taking combinations of periodic functions that also have period 2l, and then add those functions together to get that function f back, potentially, provided all of our convergence issues are worked out. So in order to do that, we're going to rely on some identities. Now I won't prove them here, but it's pretty easy to prove them. On the interval from negative L to L, cosine of n pi x over L, the integral from negative L to L of that function is 0. Now for n equals 1, we would have y equals cosine of pi x over L. So that's where you would see 1 period on the interval from negative L to L. That might look something like this. If I did a better job with my graph, this is just saying that this area minus this area minus this area is 0. This plus this equals that. So the net area under the curve is 0. Now, same thing happens with the sine function. If n is equal to 1, we have y equals sine of pi x over L. In that case, we would see this on the interval from negative L to L. Remember, our sine function starts at 0 and then it goes up and then it comes down and then it goes over here. Well, if I just traced that backwards, it would go this way. This area and this area are the same. So this area minus this area is 0. So the net area under the curve would be 0. Now these next 3 guys, I'm not going to prove, but we could easily prove this. So if we're on the interval from negative L to L, we have a product of cosine functions as our integrand. If those cosine functions have different frequencies, so if n and m are different, so you've got a different number of waves between negative L and L, or a different number of cycles between negative L and L for those guys, it turns out you get 0. And if the frequencies are the same, so we'd have cosine of n pi x over L times itself. So I'd have cosine squared of n pi x over L. I could use power reducing formulas from calculus 2 to rewrite that and then evaluate the integral. And it turns out if you do all of that calculation, the value of this is L when the frequencies of those 2 functions are the same. Now you can prove that that equals 0 using the product to sum formulas from calculus 2. Now, if I've got a product of sine functions here, you have something very similar. You'll get 0 if n is not equal to m. You'll get L if n is equal to m. And again, to prove the ones that involve the 0, you're going to use the product to sum formulas. If you're looking this up in a calc book, you want to look up the trig integrals section. of that calc book. And then for these guys that give us L, that's where we have a cosine and a cosine or a sine and a sine, and the arguments are the same. On those, you're going to use power reducing formulas to evaluate the integral. So you'll go from a cosine squared down to a 1 or a 1/2 times a quantity 1 plus cosine of double the angle. So you'll use power reducing formulas for both of these guys in order to evaluate those integrals. And you should work it out if you don't believe me or you are having trouble thinking through how you get these values. But if you use those power reducing formulas, you'll be able to evaluate the integral, plug in the limits, and then you'll get L for each of these guys. Now, if you have a product of sine and cosine functions, turns out you're going to get 0 every time. And this could be proven or shown using the product to sum formulas from the trig integrals section in Calculus 2 as well. Now, we're not going to prove those, but we're going to refer back to these when we find the full Fourier series expansion of a particular function f. So again, here's our expansion. And different books use different versions of this formula. Sometimes they include the 1/2, sometimes they don't. We will include the 1/2 as Dr. Constanda does in his textbook. Now, I'm just going to outline what we'll do, and we'll do this later in an example. The unknowns here are the a sub 0, the a sub n, and the b sub n. Again, going back to that example for Taylor series, the unknowns in this case are the coefficients, and the coefficients turn out to be equal to the nth derivative of the function evaluated at that x0, that center point of your series, divided by n factorial. But when I'm looking down here at an actual Taylor series, I'm thinking of these as the weights for the functions x to the 0, x to the first, x squared, x cubed, x to the fourth, and so on. These a sub n's, a sub 1, a sub 2, a sub 3, and so on, and the b sub n's, b sub 1, b sub 2, b sub 3, and so on, from n equals 1 to infinity. Those are the weights of those cosine and sine functions that are just cosine and sine functions with different frequencies. When n equals 1, we've got 1 cycle on that interval from negative L to L. N equals 2, we have 2 cycles. N equals 3, we have 3 cycles. And the same is true for the sine functions. So the question is, how do you find a sub 0, a sub n, and b sub n? So here's our method. It's actually pretty simple. To find a sub 0, well, first we're going to assume equality. So we'll assume that f is equal to the series. Although technically, it's not always equal to the series. We'll talk about the conditions when it's equal to the series and what the series is equal to in general. So we'll first assume that, then you integrate the entire equation once we've changed that tilde to an equal sign. Integrate the equation sort of term by term. So you'll have the integral of this plus the integral of this piece plus the integral of this piece. And actually the integral of the sum is a sum of the integrals. So you're actually evaluating this integral of this function from negative L to L with respect to x. you're kind of doing that infinitely many times, but you're sort of doing it in one fell swoop, because we will just integrate this expression with respect to x on the interval from negative L to L. Now, because of those identities, because the integral from negative L to L of this cosine function is 0, and the integral from negative L to L of this sine function is 0, when I integrate this, I'll have the integral of f of x from negative L to L is equal to the integral of 1/2 a naught, which is just a constant, from negative L to L, plus the integral of this piece, plus the integral of this piece. Those are just constants, so we can factor them out. The integral of all of these guys is going to be 0, and the integral of all of these guys from negative L to L will be 0. So this will all be gone, and you'll just have the integral of this equals the integral of that. And we'll know what f of x is, because we're starting with some function and we're trying to come up with this expansion. Since we know what f of x is, we'll be able to solve for a sub 0. So we'll end up with something like this. And I factored out my 1/2 a naught there. The antiderivative of 1 is, of course, x. We evaluate from negative L to L. So we substitute in the upper limit and the lower limit, and we subtract. So that's going to be 2L times 1/2. So we'll get a naught times L. And of course, everything else is gone because we've integrated this on the interval from negative L to L and that as well. So we get 0. And so that's going to give us this formula for a naught. 1/L times the integral from negative L to L of f of x dx. Since you know what f is, that's going to be given to you in the problem. You'll be able to solve this. Now, most professors that I know that teach partial differential equations aren't going to just want you, or they're not going to want you to just plug in your f here and evaluate this integral and say that's a naught. What they want you to do is this part here. We want to integrate the equation with respect to x from negative L to L, and then use these properties from the last page to simplify. And the reason we're doing that is because we're trying to get at the point that we know where this formula for a sub 0 comes from, so that we're not just plugging and chugging into some formula, but instead we're saying, oh, the way I get rid of that, the way I get rid of these functions and am able to solve for a naught is to integrate every single one of these terms on the interval from negative L to L. And that will allow us to find a naught. So that first, or this first pair of identities allows us to find a naught. Now, if I want to find the a sub n, which is right here, it's multiplied by a cosine function. The way I get that a sub n by itself is I need to multiply by something so that this term doesn't disappear, right? When we integrate from negative L to L. I don't want this times something else, the integral from negative L to L of this times something else to be gone. I don't want it to zero out. So the question is, what do I have to multiply this equation by if I change that tilde to an equal sign so that this function remains, or so that terms that look like this remain? Well, let's look at our identities. If I want a cosine to stick around and I don't want it to zero out after I integrate from negative L to L, I need to use this one. Because if I take a cosine and I multiply by a cosine, most of them will zero out. I'm going to get 0 most of the time, except for when the frequencies are the same. When the frequencies are the same, when n and m are equal to each other, in that case, this integral will equal L. But if I take a cosine and I multiply it by a sine function, I'll get 0. So in order to find the a sub n, we'll multiply by cosine of m pi x over L and integrate from negative L to L. So if I multiply this now, thinking of it as an equation, and I multiply it by a cosine function, I'll have f times the cosine over here, and I'll integrate that. That'll be something that I can evaluate, typically using integration by parts. And then I'll have this constant times the cosine. I'm integrating from negative L to L, but that integral is 0, so that a naught term is going to be gone. And then I'll have this guy times the cosine of m pi x over L. Well, sine times cosine, when I integrate that from negative L to L, according to this guy, I'll get 0. So the only term that will be non-zero will be this one, and then this one. So we'll have the integral from negative L to L of f of x times cosine of m pi x. And that will equal this sum, let's say just for now, the sum as n goes from 1 to infinity of a sub n times the integral from negative L to L of the cosine of n pi x over L, that was already there, times the cosine of m pi x over L, which was not there. Everything else, that guy zeroed out and that guy zeroed out because we had a cosine integrated from negative L to L, and then we had the sine times the cosine integrated from negative L to L. So we're here. Once I'm here, remember this integral is 0 whenever n and m are not equal to each other. But we'll get L when n and m are equal to each other. So that means on the interval from n equals 1 to infinity, only one of these guys will remain, and it's the one where n is equal to m. So this will actually be equal to a sub m times the value of this integral, which is L. Now, our formula has an a sub n in it, not an a sub m, but now I've got this side equals this side. I can change the n's into, or the m's into n's, because m in this case, at this point, after I've simplified that equation, that's just a dummy variable representing the frequency of that particular cosine function. So we can change the n's into m's. It won't change anything. Divide both sides by L. And we get this. So that's our a sub n. So we've got this formula for a sub 0 and this formula for a sub n. But again, we're not just going to substitute f of x into this formula and f of x into this formula. We want to show that we know where these formulas come from. So we are going to multiply our equation by this and integrate the result from negative L to L. I'm not going to show the whole thing this time, but you can imagine how we find the b sub n. Those are the weights of those sine functions. B sub n is multiplied by sine of n pi x over L. And if I look at my identities again, if I want to keep that sine function, or if I want to keep that b sub n term around, or something that looks like that, I need to multiply a sine by another sine. So I need to multiply sine of n pi x over L by sine of m pi x over L, and then we'll integrate from negative L to L. Now, I'm not going to show the whole process again, but remember, if you multiply both sides by this, on the left-hand side, you'll get this. And then the integral of this guy from negative L to L times that constant will be 0. The integral of this guy, all of those guys from n equals 1 to infinity, multiplied by a sine of m pi x over L and integrated from negative L to L, because if you have a sine and a cosine function, we'll get 0 every time. And then the only one that will be non-zero is this one. I said I wasn't going to talk through it, but I did. So we have the sum as n goes from 1 to infinity now of b sub n times the integral from negative L to L of sine of n pi x over L times sine of m pi x over L. And this guy is 0 when the frequencies are different, and it's L when the frequencies are the same. So I'll have b sub m times L, and then you can solve this for b sub m and then replace the m's with n's to get the formula for the b sub n. So b sub n equals 1 over L times the integral from negative L to L of f of x times sine of m pi x over L dx. Last formula. But again, we're still going to think through this process of multiplying by that function and integrating, and then remembering these relationships are what get us from that Fourier series expansion of f to the coefficients a sub 0, a sub n for n equals 1 through to infinity, and b sub n for n equals 1 to infinity that we're looking for. And again, those are the weights of these sinusoidal functions that we're adding together to try to get f back under certain conditions. Okay, so remember where we started. I started over here. That's the Fourier series for my function. And then I said right here, we're assuming that f is defined on the interval from negative L to L, and this is its periodic extension. So I've got a function with a period of 2L, and I'm sort of interested in that interval, not from 0 to 2L, but from negative L to L instead. And I'm extending it periodically, so it makes sense to look for combinations of these sinusoidal or periodic functions that have the same period as our function f. But really, I'm interested in adding up all of those sinusoidal functions, that constant plus some combination of cosines plus some combination of sines with different frequencies, in order to get this function back on this interval. So even though we created the periodic extension of f for the entire real line, our interest is really only here from negative L to L, or here where that original function was well defined. So let's write that down. Now it's possible that this series diverges. And it's possible that you may have a sum that is different than f of x for different x values. Let's talk about when we would expect the series to converge to f at some x values and what that would converge to. In order to get there, we need a couple of definitions. We need to talk about what it means for a function to be piecewise continuous, and for what it means for a function to be piecewise smooth or smooth on a given interval. And then we'll be able to talk about convergence in some cases related to piecewise smooth functions and piecewise continuous functions. So piecewise continuous functions F. We say that a function is piecewise continuous on the interval from A to B if it is continuous at all but finitely many points. On the interval. And this is really important, has only jump discontinuities. Remember, jump discontinuities are discontinuities where the limit from the left and the limit from the right exist on either side of that discontinuity. So it's continuous all the time except for a number of points that we can count, just a finite number of points. And at each of those points, we have to have a jump discontinuity. So here's an example of a piecewise continuous function. Maybe my function looks like this, and then like that. It has one discontinuity at this value, whatever that x value is, and it has a jump discontinuity. The limit from the left of x naught is some finite value, and the limit from the right of x naught of that function is some finite value. So this function is piecewise continuous. So if I said that this is y and this is y equals f of x, and that's x, that's a piecewise continuous function f. Now, if we had an infinite discontinuity somewhere, so maybe you've got an asymptote and the function looks like this. So this function seems to be well-defined, and you might even think it's piecewise continuous because it looks like it's got two continuous pieces. Intuitively, you might think, oh, that's a continuous piece and that's a continuous piece, so it's piecewise continuous, but that would be wrong. This is not piecewise continuous. Let's say that this is x equals 3. And the reason for that is that the limit as x approaches 3 from the right, so I'm approaching from the right-hand side from values larger than 3 of my function, which I'll label f, is positive infinity. So that's a limit that does not exist, doesn't exist in a special way. It goes to infinity. Now, Dr. Constanda in his book uses a slightly different notation for this. Rather than writing this every time, he uses this notation. He would say, or I don't even think he'd write the infinite sign like that, but referring to this limit as x approaches 3 from the right, he would write it this way, f of 3 plus. This refers to the limit as x approaches 3 from the right. Since the limit as x approaches 3 from the right does not exist or is infinite, then this function here is not piecewise continuous. So let me just write this down. This notation represents the limit as x approaches x naught from the right. And this notation represents the limit as x approaches x naught from the left. Now, sometimes in the book, he'll just use f of x plus and f of x minus to refer to the limit of the function as x approaches, or as the independent variable approaches x from the right and from the left. But I use the x naught so that to make it clear that we're talking about a specific x value rather than the variable x. So that's piecewise continuity more. The definition of a piecewise continuous function. It's continuous in pieces And all of the discontinuities are jump discontinuities like that. We don't have any oscillating continuities or infinite discontinuities. There's never a case that the function is discontinuous at a point because the limit doesn't exist. Here, the limits exist. They're just finite values from either side, of course. Now, if you have a function that's piecewise continuous, if I'm looking for the area under the curve, the area is not at all affected by what happens at x naught. Like I could let the y value be equal to that value, or I could put an open circle there and let the y value be something else, or I could let the y value be something else. That value of f at x naught will not affect the area under the curve at all. And that's important because when we are evaluating these expressions, we're integrating f times a function on the interval from negative L to L. So we want to make sure that that integral exists and is well defined. If our function is piecewise continuous, then we're good to go. What happens at this particular point does not at all affect the area under the curve. And remember that integral from negative L to L of the function represents the area under the curve, or a net area above the x-axis minus the area below the x-axis and bounded by the function. So this, let's say here, this integral from negative L to L of f exists and is independent of the values of f at the jump discontinuities. And see how we might have problems if we were dealing with something that's not piecewise continuous like that. In order to evaluate an area under the curve there, we need to use an improper integral. But if all you have is jump discontinuities with a piecewise continuous function, these integrals that we've been talking about are going to be nice. They're going to be fine. And what happens at that single point does not affect area under the curve. Let's talk about smooth functions. We say that f is smooth. It's a smooth function on AB. If f and f prime are both continuous on the interval from A to B. And that just means when you look at the graph, there are no sharp corners. This guy, well, this guy is continuous. And if this guy is also continuous, that means there are no sharp corners in the function f. So that's what it means to be smooth. Now we talk about a function being piecewise smooth. On that interval from A to B. If at least one of f and f prime is piecewise continuous on the interval from A to B. So they don't both have to be piecewise continuous. But if one of them is piecewise continuous, then we say that f is piecewise smooth. Okay. So we've got some important definitions. And we understand what they mean for the graph and their significance as far as the value of that integral from negative L to L of our function, which is going to come up when we evaluate expressions to find the Fourier series for particular functions. Now let's talk about convergence. Here's our theorem. If f is piecewise smooth, on the interval from negative L to L, then its full Fourier series, and we say full Fourier series because we're going to talk about cosine series and sine series later. If it's piecewise smooth on that interval from -L to L, the series we talked about converges pointwise. To, first of all, the periodic extension of F of course, that was a periodic extension of F to the real numbers at all points where F is continuous. And then using that notation for the left and right-hand limit, it will converge to the average of the limit on the left and the limit on the right for each jump discontinuity. Looking back at that picture that we drew earlier at the very beginning, this is our periodic extension of F, at least on that interval from -3L to 3L. If I want to know what it converges to, the series, what the series would converge to, it would converge to pretty much exactly the same function, but here at -L and 3L and 5L, and all of those odd multiples of L where we have that jump discontinuity, the series would converge to the average of these two y values. The limit here is 0, the limit there is L. So the series would converge to half of L there, and half of L there, and half of L there. Not too bad. Okay, so now let's do an example. Long video. That's what it takes to go over this topic, so we don't mind. Let's say we're asked to do this. We want to construct the full Fourier series of the given function f. And then we want to discuss the convergence of this. When I say this, I mean the series on the interval from -L to L. And then we also want to sketch the function to which the series converges pointwise on the interval from -3L to 3L. So basically, we want to sketch 3 periods of that periodic extension with, you know, those average, that average of the limit, the average of the limit of the left and the limit from the right plotted for each jump discontinuity on the interval from -3L to or -3L to +3L. So this is my function. I've got a function x on the interval from -1 to 0, and I want to use the function 2x minus 1 on the interval from 0 to 1. That's my plan. So first we're going to write down the form of the series. Well, actually, first, let's do something else. Let's sketch this guy. We're on the interval from -1 to 0 here. And we're on the interval from 0 to 1 there. So we see that L is equal to 1 because we're going from -1 to 1. So we use this to infer L. And then we'll sketch this. When X is equal to -1, Y is equal to -1. When X is equal to 0, Y is equal to 0. It's just the line Y equals X, but just a segment of that line. And then when X is equal to 0, if F were given by this function, the Y value would be 2 times 0 minus 1, or the Y value would be -1. But F is not given by this function at X equals 0. So I'll put an open circle there. That's where this line segment would start if there was a less than or equal to sign there. And then this line has a slope of 2. So it would go up 2 and over 1 to get another point on the line. Or if you prefer, you can just plug in X equals 1. You get 2 times 1 minus 1. 2 minus 1 is 1, and you would get that Y value. And then since you know this is the equation of a line, Y equals mx plus b, if you've got that point and that point, you can just connect them with a line segment. So this is our function F. And that should be an open circle. I know it looks a little funny from the way I drew it. That's an open circle. So that's the graph of F. Always a good idea to graph that function F on the interval from -L to L. And then let's graph the periodic extension from -3L to 3L. Since L is 1, this is going to be the periodic extension on the interval from -3 to 3. Now remember, when you're constructing that periodic extension, we always look at this interval from -L to L, but we don't include that left endpoint. So instead of a closed circle there, I'll use an open circle at -1, -1. Oops, and actually there's an equal sign there, so that will be colored in. And then I've got an open circle here and a closed circle there. So I'm graphing almost exactly the same thing as F, but I'm leaving off that point on the far left because we want like open parentheses there. And we're doing that so that our function only has one value at this side, on this side. So then I want to sketch this again over here. And then I'll sketch it again over here. Okay, here's Y, here's X, and this is the periodic extension of F. It's three periods of the periodic extension of F. On the interval from -3 to 3. And I guess I actually left off that last point. So -3 to 3 there. I guess technically if I wanted to include that point, I could do this. And then I could use a bracket there. Okay, so now I'm going to write down the form of the series. So F is given by, or potentially given by 1/2 A plus the sum as n goes from 1 to infinity of A sub n times cosine of n pi x over L plus B sub n times sine of n pi x over L. But we know L is equal to 1, so we can substitute that in. Okay, so now we want to find a sub 0, a sub n, and b sub n. And remember, f is given by this function over here. So to find a sub 0, we will assume that f is equal to this series. And then after we make that assumption that f is equal to the series, we will integrate everything from negative L to L. So we'll say integrate both sides of the equation. From negative L to L. So on this side, I've got an f of x. On the other side, I have, actually, I'll leave a little space there, a 1/2 a sub 0. I'll leave some space there, plus the sum as n goes from 1 to infinity of a sub n times cosine of n pi x plus b sub n times sine of n pi x. And this is what I have. I want to integrate this from negative L to L on both sides. So every term in this summation will get integrated from negative L to L. Now the integral of the sum is the sum of the integrals, so we can pull the integrals inside. And a sub n and b sub n are constants. Now remember those identities from earlier. The integral from negative L to L of cosine of n pi x is 0, and the integral from negative L to L of sine of n pi x is 0. I've got those curves shown for n equals 1. You can see that that area above the curve is matched by the area below, so that area minus that area is going to be 0. The same thing happens here, and that's going to happen for all the different values of n too. So remember, for different values of n, you just get more cycles on that interval from negative L to L, but still the area above the x-axis is matched by the area below the x-axis, and you're going to get 0 every time. So this will equal 0 for all n equals 1 through infinity. So will this. So that's nice. Now we just have the integral from negative L to L of f of x, and that equals 1/2 of a, now our a naught. Now we're integrating this constant with respect to x, so we'll get x evaluated from negative L to L. Factoring out the constant, substitute in the upper limit, substitute in the lower limit, and subtract. L minus negative L is 2L. So I'll have 1/2 times a naught times 2L. The 1/2 and the 2 reduce. And so we get a naught is 1 over L times the integral from negative L to L of f of x. And actually, this time we knew that L was equal to 1. So I could have substituted L equals 1, probably should have. So if L is equal to 1, we have a sub 0 equals the integral from negative 1 to 1 of f. And f was defined in 2 pieces. It was defined on the interval from negative 1 to 0, and then it was defined once again on the interval from 0 to 1. On the interval from negative 1 to 0, our function is x. On the other interval, it's 2x minus 1. Now from here, there are a couple of ways you can do this. You can use geometry to find this area. I can tell the area of that little triangle is just going to be 1/2, and it's below the x-axis, so I'll get negative 1/2 from this. And then this guy is going to be this area, or this area above the x-axis minus that area below, and I think I'm going to get 0. So I think a naught must be negative 1/2 just using geometry. Let's confirm it algebraically by doing the calculation. Easy breezy. Just use the power rule here. So you add 1 to the exponent and divide by the new exponent. Substitute in -1 and 0 and subtract. So you have 1/2 times 0 squared minus 1/2 times -1 squared. Over here, you can bring your 2 down, add 1 to the exponent, divide by the new exponent. The antiderivative of -1 with respect to x is just x. Evaluate that at 0 and 1. So at x equals 1, we'll have 1 squared minus 1. Then we'll subtract this evaluated at 0, which is just 0. 1 squared minus 1 is, of course, 0. Of course, this is 0. -1 times -1 is +1. So we'll have +1 times -1/2, which is -1/2. So from this, we have a0 equals -1/2. All right, cool. Now to find the a sub n, remember this is where we're starting. I don't want these cosine terms to cancel out. In order to ensure that I have an a sub n or an a sub m left after we integrate from -L to L and multiply by something, I'm going to multiply this entire equation, this set equal to f of x, by cosine of m pi x over L, and then I'll integrate from -L to L. I'm going to call that the series equation. F of x equals the series. Multiply the series equation by cosine of m pi x, and then integrate from -L to L. Okay, so we started with f of x over here. And then we have 1/2 a sub 0. We're going to multiply that by a cosine. And then we'll have the sum as n goes from 1 to infinity of a sub n times cosine of n pi x. I keep writing -L to L. I should be writing -1 to 1 because we already know what L is. And I'm going to run out of space, so I'm going to use the next line to write the rest of the series. We've got the sum as n goes from 1 to infinity of b sub n times sine of n pi x. Now we're taking this equation, this equals this plus this plus this, and we're multiplying it by cosine of m pi x over L, where L is 1. And then we are integrating each of these guys on the interval from -1 to 1 with respect to x, of course. And you can factor out the constants. Okay, now this constant, whoops, there should be a dx there, times the integral from -1 to 1 of cosine of m pi x over L. That'll be 0. Here, if you've got the cosine and sine functions on the interval from -1 to 1, that's going to be 0. So this guy is gone and this guy is gone. The only thing that is left is this side and then this piece. So we'll say that's equivalent to this. Now remember from our identities, this is going to equal 0 most of the time. That'll be 0 when n is not equal to m, but when those happen to be the same, then we'll get L, which in this case is 1. So I've got infinitely many terms here. We'll have a sub 1 times this, plus a sub 2 times this, plus a sub 3 times this, and so on. But only one of them sort of sticks around. All of those are going to be multiplied by 0, except for the one when n is equal to m. So this actually simplifies to a sub m. Now, since our formula has an n in it rather than an m, if I'm thinking of this equal to this as an equation now, I don't really want to use m, I want to use n. So I will switch back to n. Now, if a sub n is equal to the integral from -1 to 1 of f of x times cosine of n pi x dx. And our function f was defined in two pieces. On the interval from -1 to 1, it was x. So we substitute that in. And on the interval from 0 to 1, it was 2x minus 1. So we substitute that in. And you'll use integration by parts. We often use integration by parts for Fourier series. Since I've got a polynomial times a cosine function, I'll use tabular. U is my polynomial. dv is everything else. Sort of ignore that dx. I often write it in parentheses for that first line, but typically we just ignore it when we're using tabular. Differentiate until you get 0. Derivative of x is 1, derivative of 1 is 0. Anti-differentiate until you catch up with the 0. So you want both columns to have the same number of rows. Antiderivative of cosine is sine. Since I've got a k times x, we've got to divide by that k. If we were differentiating, we'd multiply by n pi. Since we're anti-differentiating, we divide by n pi. And then the antiderivative of sine is negative cosine. And we'll divide by n pi again. So I have 1 over n squared pi squared there. Then we have this, these signs on the outside that come from sort of distribution of that negative in the uv minus the integral of v du formula, if you're doing integration by parts multiple times. And that'll give you your antiderivative. So we've got this times this. Minus negative or minus 1 times this. So a -1 times that is going to be a positive 1 over n squared pi squared times cosine of n pi x. And we'll evaluate this at -1 and 0 and subtract. We use tabular integration by parts over here as well. U goes in this column. dv goes in this column. Differentiate until you get 0. Anti-differentiate. We get that of plus minus plus. Now again, this is u times v minus the integral of v du. So then you'd use integration by parts again, and then this would be your new u times v minus the integral of v du. So we'll have plus 2x minus 1 in the numerator divided by n pi times sine of n pi x. And then we have -2 times this, which is going to give us +2 over n squared pi squared times cosine of n pi x. All of this is evaluated from 0 to 1. Okay, now if I plug in 0 over here, I get 0 times something, so that's clearly 0. And over here, I'll have cosine of 0. Remember, cosine of 0 is 1. So this evaluated at 0 is just 0 plus this times cosine of 0, which is 1. So I just get that coefficient right there. And then we're subtracting this expression evaluated at x equals -1 now. So at x equals -1, I'll have -1 over n pi. This is sine of -n pi then I have 1 over n squared pi squared times cosine of negative n pi. And we'll talk about how to simplify these two guys in just a moment. Over here, when I substitute in x equals 1, I have 2 minus 1, which is 1, times sine of n pi, plus 2 over n squared pi squared times cosine of n pi. And again, we'll talk about what that is. And then we're subtracting this expression evaluated at x equals 0. So if x equals 0, I'm subtracting negative 1 over n pi times sine of 0 plus 2 over n squared pi squared cosine of 0. Now, sine of 0 is 0. Cosine of 0 is 1. I used that earlier here. Now it's helpful to think about sine and cosine, or sine of negative n pi and n pi. Remember what our sine wave looks like. It just continues. That's 0, that's pi, that's 2 pi, that's 3 pi, that's 4 pi. I think we can all see that if this is y equals sine of x, at all of the multiples of pi, and that's what we're treating n as here. Remember, n is a counting number 1, 2, 3, and so on. We're going to get 0 for sine of n pi. And if we have negative sine of n pi, well, that's just on the other side, we'll still get 0. This pattern continues. So this guy right here is 0, and this guy is 0. Now, a couple of things with the cosine function. Cosine is an even function. So just as a reminder, cosine looks like this. So I'll call that negative 2 pi and that 2 pi. Now remember what it means for a function to be an even function. That means if we go x units in this direction and x units in this direction, and we find the y value there and we find the y value there, one of those is called f of x and one of those is called f of negative x. That's if that's x and that's negative x, those y values are the same. So for cosine, that's cosine of negative x equals cosine of x. And that's because cosine is even. Well, and that means, or that in that case, that means my cosine of negative n pi is equal to cosine of n pi. So these are really the same thing. And then the question just becomes, what is the cosine of n pi? Well, let's look at our cosine wave. And I think I'll go out at least one more period like that. So that's pi, that's 2 pi, this is 3 pi, that's 4 pi. And it continues. So cosine of n pi when n equals 0 is cosine of 0, which is 1. Then we've got 1 pi, 2 pi, 3 pi, 4 pi. Notice the cosine functions going from 1 to negative 1 to 1 to negative 1 to 1 as we take on even and odd multiples of pi inside that cosine function. So with that in mind, we see that cosine of n pi, where n is an integer, so n is never a fraction, it's just a positive or negative number. It's a whole number. It's it's a natural number, it's an opposite of a natural number, or it's 0. In that case, this is an alternating negative 1 or 1, negative 1, 1, negative 1, 1, negative 1. When n is 0, we get negative 1 to the 0, which is 1. So this is the same as negative 1 to the n. This is for an integer n, for all integers n. So when I see that cosine of n pi, and that tends to come up a lot when we're doing these Fourier series, I don't leave it as cosine of n pi. It's actually an alternating sign, SIGN sign. That's a -1 to the n, and that is a -1 to the n. So with that in mind, our a sub n is this. We just need to simplify it. So I have 1 over n squared pi squared. And then I have 0. And don't forget, we're subtracting this. So I'm subtracting, I've got a -1 to the n over n squared pi squared. Over here, I have a 0 and a 2 over n squared pi squared times -1 to the n. And this one is 0, and that's a 1, and I'm subtracting that. So I've got 2 over n squared pi squared. That's my a sub n. Of course, I want to simplify it. I've got 2 of these guys here, and I'm subtracting 1 of those. So that means I only have 1 of them. And that's taking care of these 2 guys, the terms that had the -1 to the n in them. And I have 1 of these, and I'm subtracting 2 of those. So I have -1 of them left. So that is my a sub n. All right, I think we're almost done. We have our a sub 0 and our a sub n. Now we need to find our b sub n. On b sub n, we're going to multiply our series equation by sine of m pi x over L, where L is equal to 1, and integrate from -L to L. Okay, so we have f of x on this side, and I'm going to multiply by sine of m pi x, and then I integrate from -L to L. Remember, we were saying that f of x is equal to 1/2 a naught plus a series. I'm going to multiply that by sine of m pi x over L, where L is 1, and integrate from -L to L. And actually, again, L is 1, so I can just integrate from -1 to 1. I keep forgetting to do that. It's okay if you do. You can always substitute your ln later. And then we'll have the sum as n goes from 1 to infinity of the a sub n times cosine of n pi x. I'll multiply that by sine of m pi x. Integrate from -L to L. You can factor out the constants. And then we have a series for the b's, and normally I would write that all as one series, but because I'm running out of space, I'll do that on the next line. I have the b's times the sine of n pi x, and we multiply this by sine of m pi x, so that one of these b's would remain after that integration. Okay. So we know to do that, and then we say, remember, the integral from -L to L of sine of m pi x over L is 0. In our case, L is 1. That's that identity that we talked about before, and it just has to do with the area above the x-axis and the area below the x-axis, exactly canceling for all of those sine waves of different periods or different frequencies. Now, if you've got a sine and a cosine multiplying each other over here, that turns out to be 0. And remember, this guy turns out to be 0 most of the time when n and m are not equal to each other. But when n and m are equal to each other, that's a sine of n pi x times a sine of n pi x. So you've got 2 of them, sine squared. You can use your power reducing formulas, and you could use that to prove that this is equal to L, which happens to be 1, when n and m are equal. So we have this, the integral from -1 to 1 of f of x times sine of m pi x is equal to this, which is going to be 0 most of the time from n equals 1 to infinity, except for when n equals m. Then this will just be a 1. So we're taking 1 and we're multiplying by b sub n when n is equal to m. So for that particular case, m, we're multiplying by 1. The rest of the time we're multiplying by 0. So we just get the 1 b sub m. Now this m now, if I'm looking at this equation, is just a dummy variable. So I can change out the n or the m for an n and say that's my b sub n. I just want to solve for it. So the integral from -1 to 0 of f, which is x, times sine of n pi x. And then on the interval from 0 to 1, my function f was 2x minus 1. And we're multiplying that by sine of n pi x. It's just like last time, we're going to use integration by parts for this guy and this guy. We'll use tabular. Here, u is your polynomial, dv is everything else. So u is x. dv is sine of n pi x. We sort of leave the dx off to the right like this. You differentiate until you get 0. So you get a 1 and a 0 there. In this column, you anti-differentiate. The antiderivative of sine is negative cosine. Since we've got a constant multiplying our x, we'll divide by that constant out front. Then the antiderivative of cosine is positive sine. Here we'll divide by n pi again. This negative from before is carried down, so we end up with an n squared pi squared in the denominator. And then we have that plus minus plus here. So the antiderivative of this function is this times this plus this times -1. That's an antiderivative. We're not going to worry about the plus c because we've got a definite integral, right? So we have negative x over n pi times cosine of n pi x. And that's -1 times a negative n squared, or 1 over n squared pi squared. So we'll have a positive 1 over n squared pi squared times sine of n pi x. And we're evaluating this from -1 to 0. That's the plan. We'll do that in a minute. Let's do the integration by parts for this guy. It's not too bad. U is our polynomial. dv is everything else. Anti-differentiate. Anti-differentiate again. Every time you get an extra n pi in the denominator. Make sure you're checking your SIGN signs for those antiderivatives. You can always differentiate to check. Derivative of this is this, derivative of that is that. So we're good. We know we're on the right track. And then when you have multiple terms, don't forget your parentheses. We've got that times that plus this times -1. That's an antiderivative. We won't worry about the plus c because we're dealing with a definite integral. So we've got a 2x minus 1 over here. And then this time we have a negative in front of that 2x minus 1 divided by n pi times cosine of n pi x. And then this times this is a negative times a negative, so that's going to be a positive 2 over n squared pi squared sine of n pi x. Evaluated again from 0 to 1. All right. Now, if I evaluate this expression at 0, I've got 0 times something, which is 0, and then I've got something times sine of 0, which is 0. So we just get 0 at that upper limit. Now for the lower limit, when I substitute in -1, I've got a negative times a negative. That's going to be a positive 1 over n pi, but we're still subtracting that, so that negative still needs to be there, times cosine of negative n pi, which we know is the same as cosine of n pi. And then we have 1 over n squared pi squared times sine of negative n pi. And sine of a multiple of pi, whether that multiple is positive or negative, is going to be 0. Our sine function crosses the x-axis at pi, negative pi, or 0, pi, 2 pi, 3 pi, 4 pi, and all the other ones, the negative pi, negative 2 pi, negative 3 pi, and so on. And cosine of negative n pi is the same as cosine of n pi, which we've already discussed. That's negative 1 to the n. That's this expression at 0 minus this expression at negative 1. Now we want to evaluate this guy at x equals 1. So we'll have 2 minus 1, which is 1, times negative 1. So I have negative 1 over n pi times cosine of n pi plus 2 over n squared pi squared times sine of n pi. And then if we evaluate this at x equals 0, well, we end up with 1 over n pi times cosine of 0, which we know to be 1, plus something times sine of 0, which is 0. So I'll just leave that as that times 1, which is just itself. Okay. And cosine of n pi again is negative 1 to the n. Sine of n pi, sine of a multiple of pi, is 0. Because of these things that we talked about up here. Let me write that down. Sine of n pi is 0. Cosine of n pi is negative 1 to the n. And we also have this identity. If you see cosine of a negative angle, you just get rid of that negative because it's an even function. Or negative variable. Get rid of that negative in the variable. Okay. So that's our b sub n. It's just a little messy, so I will write that down here on the next line. I have negative 1 times this. So there's a negative 1 to the n over n pi. And then that's just 0, so that's gone. Over here, I have a negative 1 to the n over n pi. And that's 0. And then we're subtracting 1 over n pi. So I've got a negative 1 of those and another negative 1 of those. So I have negative 2 of those. And I'm subtracting 1, and we're dividing all of that by n pi. All right, so that means we've got the a sub n, the b sub n, and the a sub 0. That's exciting. I hope we did this correctly. I hope I didn't make any little SIG and sign errors. That means our Fourier series is this. Just writing down my formula. And I will now substitute in my a sub 0. I believe we found to be negative 1/2. And then I'll substitute in my a sub n. And a sub n turned out to be negative 1 to the n minus 1 over n squared pi squared. All of that is multiplying that cosine of n pi x. And then the b sub n was this guy. So I have negative 2 times negative 1 to the n minus 1 over n pi times sine of n pi x. Provided we didn't make any algebra mistakes anywhere. So we've got negative 1/4 plus this. And I'm just going to rewrite that now. All right, so that is the series, the full Fourier series for f of x. And remember, f looked like this. Now, the question said, the problem statement said this. Construct the full Fourier series of f. We just did that. and discuss the convergence of the series on negative L to L. So remember, this series that we just constructed is going to converge to the periodic extension of f on all of the points where f is continuous. So our series will converge to this here and here and here and here and here and here and all of those intervals from n to n plus 1 where the function is continuous. But at the discontinuities, the series will converge to half of, or the average of, the limiting value on the left and the limiting value on the right. So we have the average of 1 and -1 here, which would be 0, or the average of 0 and -1 here, which would be -1/2. So our series converges to, let's draw this periodic extension plus the extra points for the discontinuities. We want the function to which the series converges pointwise on the interval from -L to L, or -3L to 3L. In this case, L is 1, so from -3 to 3. So we'll say the series converges to this function. And it's very similar to the periodic extension of f, but we've got some extra points in there. So I had an open circle here, and a closed circle there, an open circle there, and a closed circle there. And we'll see that same pattern over here. Or actually, this would be the periodic extension. Something wrong with these, so I'll have to fix that in just a moment. So in black, we have the periodic extension of the function on the interval from -3 to 3. Now in red, I want to sketch the function that the series converges to. So when I say the series converges to this function, it's not the black function. I'll say the black represents the periodic extension of f. On the interval from -3 to 3. And the red will represent the function the series converges to. So the series is going to converge to this whenever this is continuous. So I have an open circle there, and an open circle there, and an open circle there, and an open circle there. Open circle, open circle, open circle, open circle. It's kind of hard to tell that those are supposed to be open. Maybe I should draw it on a different graph. I think I will. Well, maybe we just know that each of these guys are supposed to be open. That's open, 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 open. I think I said open enough, but the function the series converges to also converges to these points. At -3, it's going to converge to the average of this limiting value and this limiting value. That's a 1 and a -1, so the average is 0. Here, the average of those two limiting values, 0 and -1, is -1/2. So we'll have 0, -1/2, 0, -1/2. The next one would be 0, and so on. So maybe that's not the best picture of that. But if you remember that all of these guys are open on the function the series converges to, then you're good. Then it says, discuss the convergence of the series on negative L to L. So we're just focused on this interval right here from -1 to 1. So we'll just say the series converges to this. Well, from -1 to 1, or actually, let's do this. At x equals -1, the series converges to 0. And on the interval from -1 to 0, the series converges to x. And at x equals 0, the series converges to -1/2. Oops. Oh, excuse me. And on the interval from 0 to 1, the series converges to 2x minus 1. And then at x equals 1, the series converges to 0 again. I guess I could have listed x equals 1 and x equals -1 on the same line, so I didn't have to have 5 of these. I could just have 4. But you get the idea. It's converging to half, or the average of those limiting values, there, and there, and there. And then it's converging to that function on the intervals where the original function f was continuous on the interval from -1 to 1. So that's how we do that. Now, if you're interested in how this approximates this function, because typically you're not going to take infinitely many terms, you're just going to take a finite number of terms. You might write this out for n equals 1, n equals 2, n equals 3, and then graph it along with the function f, which actually looks better over here. That looks like this, and see how well this combination of sine and cosine functions and that constant -1/4 out front, to see how well this actually matches that function. So I'm going to pause my video briefly and write out a couple of those series approximating f, and then maybe we'll graph those on Desmos. I think on second thought, I'm not going to graph these on Desmos this time, but I did want to show you some partial sums of their series. When n equals 1, we would just get this from substituting n equals 1 over here. So that's a cosine with a certain frequency, and that's a sine with a certain frequency. You're just going to see one full cosine wave on the interval from -1 to 1, and you'll see one cycle of this sine wave on the interval from -1 to 1. If I take this much of this function and this much of this function and I add -1/4, I'm going to get something that's close to the function f. But if I want a better approximation, usually that's how it works, we'll take more terms. So s sub 2, that's the second partial sum of that series. I would get the first partial sum plus the expression that I get when n equals 2. And when n equals 2, we're going to have -1 squared, which is 1 minus 1, which is 0 here. So when n is even, the cosine functions are actually gone. And we're just left with a sine function from over here. So when n equals 2, I get that sine function. When n equals 3, I get the second partial sum plus these two functions. So again, we're taking these linear combinations of cosine and sine functions. We're just multiplying them by the appropriate constant. And we're saying if we add these together, this series turns out to converge to this periodic extension. Or if we're interested only in the interval from -1 to 1, which we typically are, it's going to give us our function on the interval from -1 to 0 and the interval from 0 to 1. And it's going to be the average of the limit from the left and the limit from the right at the 3 points of discontinuity. And those are points of discontinuity of the periodic extension of the function. But you should check it out if you want to. After you graph, or after you write these out, or maybe use Mathematica to write this, maybe take the sum as n goes from 1 to m, and then just let m take on different values. You can graph each of these functions and see how close they are to this guy right here. And the idea is, in the limit, we would actually get this back. The series converges to this. So that's the end of our conversation about full Fourier series.